Okay, hi everybody. The purpose of this lecture is to just give you a little tiny introduction to some of the basic terminology we're going to need in studying ODEs. We're going to look at how you classify differential equations. And in general, I will do my own videos, but for this simple short introduction, I'm going to go ahead and use the notes from Boyce and DePrimo. Basically, when you look at a differential equation, an ordinary differential equation, it means that you are looking for an equation involving the derivatives of a function of a single variable. So in this one, you can see that v is a function and v depends on t because we're talking about dv dt. Another example of an ODE is very similar to that one they just wrote. So let's go down to this next one. This function q is a function of t only, presumably time. But this differential equation not only involves the first derivative of capital Q, but also the second derivative of capital Q and the function capital Q itself. So that's perfectly okay. That's still an ordinary differential equation. Whoop, gotta do it this way. So if you had a function which depended on more than one independent variable, say a function u, which depends maybe on x and t, then an equation which involves the partial derivatives of that function is called a partial differential equation. We will not be touching on those in our class. That's for a later class. That's a completely separate subject. But the class on PDEs, which is very interesting, builds on the material in ODEs that we are going to cover this semester. So two famous PDEs are the heat equation and the wave equation. So in this first one, in the heat equation, U represents the temperature in a medium, and X usually represents position, and T represents time. So U of X and T tells you the temperature in the medium at position X and time T. And it's beyond the scope of this course to explain why this equation models the way heat flows in that medium. Down here in the wave equation, the unknown function u is a position, again, is a function of x and t. So x is position, t is time. And here u represents displacement from an equilibrium. But again, that PDEs are my specialty in research, but that's beyond the scope of this class. Later on in the course, we're going to study things that involve more than one ODE, or what we call a system of ODEs. So a very well-known terminology-wise, even if you don't know much about ordinary differential equations, is predator-prey equations. So you have two unknowns, u and v, two unknown functions, and both are functions of t only. So here, X and Y are the respective populations of predator and prey, and A, B, C, and I don't know why the gamma and the alpha are out of line, but they are in these notes. So they depend on the particular species being studied. So we'll talk about systems of predator-prey equations later. And actually, I see a typo here. This should be dx dt, and this should be dy dt, not u and v. There's only u and v, x and y are functions of t, and there is no u and v. This should be dx dt, and this should be dy dt. Okay, so we know that basically up to this point, the thing I want to mention to you is we will be studying equations involving derivatives of a function of a single variable. And later on in the course, we'll study systems of such equations. Okay. We need to get a little terminology set so we understand each other when we talk about what we're doing in these differential equations. So if we write an ordinary differential equation can be written as f of t, which is the independent variable, and then y and all of its derivatives are functions of t. So this is again a typo. This should say where y is y of t. It's a function of t only. Okay. So for example, you might have an equation that looks like y triple prime plus 2 times e of t, e to the t rather, y double prime plus y times y prime equals t to the fourth. So this is an ordinary differential equation. And when we look at an ODE, we call the order of the differential equation the highest derivative that we see in that equation. So in this first one, you see y to the n is involved. This would be an nth order differential equation. Here, the highest derivative we see is a third derivative. So we would call this a third order ODE. Okay. Um, if you we would like to say it's always possible. This is not always true, but we won't deal with ones that aren't of this form. If that you can solve for the highest derivative that appears in the equation. In other words, we can write that if it's an nth order equation, we can write yn, the nth derivative of y, that is, as a function of t, in terms of the independent variable and all the lower order derivatives of y, including the zeroth order derivative, which is the function y itself. Okay, so in other words, in this class, we will only be studying differential equations where you can isolate the highest order derivative. That's not always true in ODEs that come up in real world applications, but for us, that's going to be true. Okay, another thing we want to do is say whether an equation is linear or nonlinear. So what's that going to mean? Let's try that again. A differential equation of this form, right up here at the top, is called linear if you can really write it as the form that you see right here. Okay, now what's special about that? What makes it a linear equation? Notice that the coefficient of y and all the derivatives of y only depend on t. They do not, the coefficients of these terms do not depend on the function y itself. So if you look down here in this first equation, numbered 1, the coefficient of y prime is 1. That's a constant that doesn't depend on y. The coefficient of y is 3. That's a constant that doesn't depend on y. So this is a linear equation. Let's look at number 2. The coefficient of the second derivative is 1. That's good, doesn't depend on t. The coefficient of y prime is 3 times e to the y. That depends on y. So this equation is not linear. Once you have one term in an equation that depends in front of that depends on y in front of the derivative of y or y itself, that's all you need to make the equation nonlinear. Okay, let's look at number 3. What's the coefficient of y prime? That's 1. That's okay. What's the coefficient of y prime? 3. That's okay. Doesn't depend on y. What's the constant term here? 2t squared. That doesn't depend on y. Not constant term, but the one that doesn't, there's no y in it. That's a linear equation. In this case, in example 3, the right-hand side here, the g of t, would be the 2t squared. Okay. And now you look at these other equations. Here you have a fourth derivative of y with respect to t, whose coefficient is 1. That's good. The second derivative of y with respect to t has a coefficient of minus t. That's okay. You have a constant term here. That's 1. That's okay. And an inhomogeneous term, or a right-hand side, that g of t is t squared. That only depends on t. That's okay. So that's linear. When we go to number 5, we run into two problems. First of all, this is not an ordinary differential equation because you see partial derivatives here, derivatives of u with respect to y and derivatives of u with respect to x. So this isn't even an ODE. So we're not going to touch on things like that in this class. But just for the record, this would be a nonlinear PDE because notice not times the UYY term, you have U. So that would be a nonlinear partial differential equation. And similarly here, because you have a UXX and a UYY, so it's a PDE, not an ODE. And notice the coefficient of UYY involves U. So that's nonlinear as well. Okay. Um, what do we mean by a solution of an ODE? We mean a function that satisfies the equation. That's all. You call something a solution of the ODE if it actually satisfies the ODE. That's not rocket science. That's pretty easy. The problem is it's not always easy to find the solutions. So what we're going to learn in this class, especially early on, are recipes to solve lots of different kinds of ODEs, but special kinds. You can't solve every possible ODE. There are some that just don't have solutions you can write down. So the one thing you should do is maybe pause this and check for yourself that if you look at the ODE, y double prime plus y equals 0, that these three functions all satisfy that same ODE. Let's talk through this first one. Suppose you look at y1 of t is sine t. What's the derivative of sine? Well, it's cosine. What's the derivative, the second derivative of sine? It's minus sine. So the second derivative would be minus sine t plus y, which is sine t. And so clearly those two add up to 0. So y1 is a solution of this ODE. And I'll leave you to check, pause this video and check that y2 and y3 are also solutions of this ODE, which show you that sometimes you have more than one solution to an ODE. Okay. So 3 big questions when you study actually not only ODE, but PDE too, is the questions of existence, uniqueness, and then how do we find it if we have a solution? So what do you mean by existence? First of all, is there a solution to your ODE? Well, we're going to have to investigate that. And then secondly, if you have a solution, is there only one? That is it unique? So existence, uniqueness. And if there is a solution, how do you find it? Can you use methods, some of the methods we're going to learn in this class to do it? Could you do it by numerical approximation? There's a method of power series, which we won't get to in this course, but you get to in more advanced courses. And so there are lots of interesting ways to find solutions. And actually, there's a third, another piece, another question that's very important, and it's called, does the solution depend continuously on the initial data? And we'll talk a little bit about where that goes wrong in the next couple of slides. Okay. All right, so let's talk a little bit about the history of the subject. Basically, everything about calculus, and ODE is really a part of calculus. In reality, differential equations, the way we're doing it, should be called calculus 4, but okay, we call it differential equations. And Newton's the father of calculus, so it's not surprising that this subject goes back to Newton in the late 1600s, early 1700s. Leibniz was also one of the founders of calculus. He worked in Leipzig, Germany. He's the one that invented that dy dx notation that we're also familiar with. And he invented separation of variables and first order ODEs. But the Newton is more well known to the general public. If you take calculus, you know not Leibniz's name, but general people know Newton's name, not so much Leibniz, mostly because Newton did so much physics, but he was just a really brilliant scientist. And an interesting fact about Newton is his birthday is December 25th. So he shares a great birthday. Okay, Bernoulli, Jakob and Johann Bernoulli were Swiss mathematicians. They did a lot of the foundations of ODE. We'll see certain equations are named after Bernoulli. We'll learn how to solve those. Daniel Bernoulli was a son of Johann, and he did a lot of work on PDE. If you take a PDE course, you'll see Bessel functions. Bernoulli did a lot of that work. Another big name in the subject for us, notice that all of this started in the late 1600s through the end of the 17th century. Most of what we know, what we're going to study, was known by the end of the 17th century, I'm sorry, the 18th century, by the end of the 1700s. So Euler was another Swiss mathematician, and he was possibly the most prolific mathematician of all times. Yeah, there are some modern day ones that might contest that, but anyway. He formulated problems in mechanics into mathematical language. He developed methods of solution, um, uh, Euler-Lagrange equations. If you continue your study into different kinds of engineering or science, and you have to study any kind of problem that you want to maximize or minimize a quantity in terms of calculus, usually you end up having to do it by deriving the Euler-Lagrange equations. He's also known for his work on exactness of first order ODEs. We'll learn what exact equations are in about 2 weeks, integrating factors in about 2 weeks. Linear equations with constant coefficients will be this week, the later video that you're going to watch. He developed some numerical procedures, did lots of work on PDEs and the calculus of variations, which is that maximization, minimization thing I was talking about. Another famous name was Lagrange. He was raised in Turin, but he was mostly self-taught, and he was just a young genius. He's famous for all sorts of things. This is just one of the tiny bit of what he's known for. Okay. Um, Another famous mathematician was Laplace. He was raised in Normandy, France, which is my absolute favorite place in the world. If you ever get a chance to go to Normandy and be along the coast and look at all the history, it's really amazing. He did a lot of celestial mechanics. Laplace's equation in PDE governs electrical currents. It comes up in all kinds of uh, applications. And the Laplace transform, which we'll study later in this semester, is named after him. So, and just as a little personal aside about Normandy, I mentioned that I'm a runner. I've run lots and lots of marathons, and I did the D-Day marathon in Normandy 4 times. It was wonderful. Beautiful place to visit. Okay, by the end of the 1700s, most of what we are going to study was already known. In the 1800s, people who were interested in differential equations began to look at the theory more precisely and to answer questions of existence and uniqueness for equations where you could no longer write down explicit solutions. And then they began to study classes of ODEs where the formula for explicit solutions, if you can find it, is quite complicated. And those kinds of things come up in physics and mechanics all the time, even though they are incredibly complicated to write down. So things like Bessel functions, which come up in if you're studying problems where you have spherical symmetry. Chebyshev polynomials, they come up a lot in probability theory. Legendre polynomials come up again in, I said Bessel functions for spherical symmetry. That's for circular symmetry. Legendre polynomials come up for spherical symmetry. Hermite polynomials and Hankel polynomials, again, come up in many physical problems with certain kinds of geometrical features. The computational results were an element in the discovery of chaos theory, and Edward Lorenz was developing weather prediction models when he observed different results upon restarting a simulation in the middle of the time period using previously computed results. So the point is not so much that we're going to focus on this, but just to give you an idea that we are learning new problems to you, but these were problems that were well understood in the 17 and 1800s. And with that, we will end this lecture. Okay, thank you.